So what we're going to have a look at here is to find the Laplace transform of the derivative of our function with regards to t. Now there's a couple of rules I've set here to help us with this, so we can have this as a valid representation. Our function, first of all, is continuous. It's what we need for our Laplace to start with. And our t is in the range of 0 to infinity. Then our derivative is also following the same rules. So that is also continuous, and from t is from 0 to infinity. And our variable s for our Laplace transform, it's an increasing s. And it's also continuous. So that's a few rules there before we set out this proof for this to be valid. Now, the Laplace transform of what we're trying to find here is of the derivative. So let's just set that up in its normal format. So the Laplace transform of the derivative, so that is usually set out into some kind of integral. So what I always set them out as is the limit as t approaches infinity. So that's capital T. You'll notice here we've got lowercase t, so I'm going to explain that in a moment. Now that goes from 0 to t. That's our parameter of integration. So t is our basically approaching infinity. And then we have the exponential function e to the minus st, and then whatever is on the input of the Laplace. So here we've got f prime of t, and then integrate with regards to t. That's the standard way to find the Laplace transform of any particular function. Okay, now here with these here, I don't know what f prime of t is, so I'm going to need integration by parts. So integration by parts, now there's a standard formula which I like to use for that, and it's the integral of u dv. So this would be my u dv, and then that equals uv minus a new integral of v times du. So I just need to work out what my u is and my dv first. Well, u here, I need to take the derivative. Well, this is the easiest one to take the derivative in terms of as a representation. So let u equal e to the minus st. So that's that one. So let's now take the derivative of that. So now du equals, well, the derivative of that with regards to t is minus s times what we have originally. So that takes care of the derivative. Now dv, I'm left with my f prime. So dv equals f prime of t. So therefore v, by the fundamental theory of calculus, v is just going to be my function of t. So that's what we've got there. So now what I'm ready to do now is just plug that into my integration by parts formula and find out what this can become. So now I've got the limit as t approaches infinity. So now I've got u dv, which is that. So it equals uv. So uv is e to the minus st, e to the minus st, and v is f prime, f of t, my function at t. So that's my first part. So that's uv, that's part of my answer. So this has to be evaluated over my range of integration. So that's from 0 to t. Okay, and now I've got the new integral. So minus the integral of v times du. So v is f of t and du is this one. So minus s e to the minus st, f of t and dt. So now we've eliminated our derivative of our function. So now we've only got it in its normal representation. Okay, so now let's put the range of integration into there, and let's see if we can simplify some things up. So the limit here applies to everything inside this right hand side here. So e to the minus st, let's work this out and evaluate it from 0 to t. So we've got the limit as t approaches infinity. Let's work this first one out. E to the minus st, so plug in capital T for this one. So e to the minus st, and then our function is evaluated at this capital T. Okay, and now subtract it for when t equals 0. So now I've got e to the minus, well, multiply this all by 0, we just get just an e to the 0, and then f of 0. So that takes care of that. Now here, let's simplify this integral up a little bit. So t is the variable of integration, so this s can come out to the front, as can the minus sign, and then this minus sign will cancel out, so we can now add s times this integral. So then we're left with e to the minus st, f of t dt. Okay, right, let's deal with this bit first. So t approaches infinity, so we want the limit as t approaches infinity. Well, if this approaches infinity, e to the negative infinity, that's going to approach 0. So this is going to cancel out, so that will go. And then we've got minus e to the 0, f of 0. Well, e to the 0 is just 1, and then f of 0, we don't know what that is. We can't evaluate it at 0 because we don't know what the function is. So all I'm left with now is minus our function at 0. That's all I can put for that so far. Okay. Now here I've got s, so that's got to stay. But this here, this is looking very similar to what I have here, except for my derivative is the input inside here. Here I've got the function. So therefore this is the same as a Laplace transform representation by integral. So I can add s times the Laplace of my function f of t. So let's write that in there. So f of t. Okay, so therefore we seem to have got to our solution here, because our integral here does not need to be calculated because that's the representation of Laplace transform. So now let's rewrite it as s times the Laplace of f of t minus, we've got the minus sign here, the value of the function at 0. And that's where we could stop. So that's our Laplace transform of our derivative for any function when we're trying to use for linear differential equations. So there we go.